Right, so let's talk about A-star pathfinding algorithm. So A-star pathfinding algorithm's goal is to find the most efficient path between 2 points, mainly start to target node, within a navigation grid. So this A-star pathfinding algorithm usually used in computer games and other AI systems. So it has a very good performance and relatively good accuracy as well compared to the baseline algorithms like Dijkstra. A-star is much more better. And it guarantees the optimal paths when the proper configurations has been applied to the algorithm and its grid. So what's the problem definition? Well, the A-star pathfinding algorithm basically solves how we can find out the path from start location to target location, and mainly the navigation grid can consist blocked or non-walkable areas as well. So this A-star pathfinding algorithm should be able to avoid those blocked or non-walkable areas and find out a proper path from start to target location. And that chosen path should be shortest and the most efficient route relatively to the overall routes that it can be reached from source to target. So what are the inputs? Well, we have to provide the navigation grid, because that's the grid ultimately we perform the path finding, and we have to simply pass the start coordinate and the target coordinate. So the navigation grid could be a n by n matrix. So if you remember at the introduction also I mentioned this. So this navigation grid could be n by n grid, and the start coordinate is usually known as S, which is some x1 y1 location, and the target coordinate is again some x2 y2 location on the navigation grid. Okay, both of them are within the navigation grid. So if I make this as n, these coordinates are on the navigation grid, right? And ultimately the output is the ordered list of positions representing the path, which means from start to target, what are the all possible intermediate coordinates within that navigation grid, which can ultimately perform a path, right? So it could be like xi, yi up until to some xj, yj path along the navigation grid. Okay, right. So in the representation of the navigation grid, it could be something like this. So these are like some blocks or blocked areas, or it could be like non-walkable grid cells. Unwalkable grid cells, and these are good to go walkable cells. Okay, and this is the start node, this is the target node, and this is the path. This is the first cell to be reached, second cell to be reached, third cell to be reached. Likewise, it goes up until to here, right? So the path is something like this. Of course, the first element is the source node, and the last element is the target node, right? Actually, this should be like, this should include like 9, 4 as well, but it's totally fine. Like once we reach to 9, 3, after that it is the target node. So the path could be something like this, right? And this is one of the optimal path. Likewise, there could be another optimal path within the grid as well, based on the location of the start and target. Okay, so what are the key codes used in A-star algorithm? So this stuff I mentioned earlier on the heuristic section, because you need to be familiar with the heuristics in order to apply the A-star algorithm properly, right? So in the heuristic section, I mentioned that if you are using cardinal direction movements, we have to use the Manhattan distance heuristics to perform the distance approximations. And if you are using the octile movements, which means the movement can be either up, down, left, right, or any other intermediate state. So if you're performing the octile movement, then the heuristic should be octile distance heuristic. Okay, and based on that, we have to calculate the F cost to perform a pathfinding. Okay, so we have discussed all of this stuff earlier. So G means basically the distance traveled from start to current node, or it could be considered as the current cost from start, and the H means estimated distance from current node to target, or else you can think like the cost to be spent from current to target, and that is the H, that's the G. So if you take the addition of this G and H, you will get the total cost for that specific path. Okay, so it could be something like this. This is our start position, and this is our current position, this is our target. So this is the cost or the distance that you have been already traveled, which is G, and this is the cost that you have to be traveled or yet to be traveled, which is H. So if you take the addition of these two costs, it will give the total cost, or else F. Okay, and the goal of A star is basically find out the lowest F cost, right? Because there could be having multiple F values or the paths, but based on those paths, we have to find out the shortest path, which is ultimately the optimum path, which has the lowest F cost. Okay, so that's the goal of A star pathfinding algorithm. So there are several data structures that we use within the algorithm. Again, in the previous sections, we have covered these min heap and priority queue related topics, because of we need to get familiar with those data structures if we are implementing a proper optimized A star pathfinding algorithm. Because internally, the algorithm uses these sort of data structures to store and manipulate data. So in the A star algorithm, there is typically three types of data structures. So first we have open set to represent what are the nodes that has been already discovered but not yet processed, right? Which are typically used as a path, and this is usually implemented as a priority queue or a min heap for the performance, because within the open set we always have to determine what's the lowest possible cost for a given path or a given cell. So in order to determine the lowest cost, we have two options. Either we have to sort the entire list, or else we can use a priority queue like data structure, which by default return the lowest minimum value. Okay, so this is actually not that much performance, right? This has like at most O n squared time complexity, or else O n log n time complexity if you are using some greedy search sorting algorithm. But for the priority queue, in the worst case also it has the O n time complexity, which is a linear time complexity, relatively much more faster than the sorting algorithms. So that's why we have to use some efficient data structures for the performance of the A star pathfinding algorithm. Okay, because the A star pathfinding algorithm will be called in many times at the gameplay. So if our algorithm is not optimized, what will happen is that the overall performance of the game will be dropped as well. So always make sure that you can implement your algorithms, but they should be optimized as well. Okay. Right. So that's the first type of data structure, which is open set. And the closed set is the second type, which is the nodes that have been already evaluated, which means they are not going to evaluate again whenever we are applying the algorithm. So this is sort of like a already visited node list, which we stores in an array or map. And whenever we are performing the algorithm, we just simply make a lookup for this array and determine whether that specific cell is within the array or not. If it is within the array, then we are ignoring it. Otherwise, we are considering it for the algorithm. So we can implement that data structure as an array or even a binary map. And the second, that's the second type. And the third type is basically navigation grid, which we have been already discussed. Basically, we have to store all the possible nodes with their type, which is whether they are walkable or non-walkable, or are there obstacles or some walkable grid cells, and what are the costs that needs to be spent to work on that specific grid, and the approximate or the relevant neighboring cells or the parent links. So the navigation grid should store all of this data, and it can be implemented as an array or a map. Okay. So currently we have been implemented the grid as a map, if you remembered. So basically the data structure would look like this. And the first cell, actually in a map, actually we have a key value pair. It's a KB pair data structure. As a key, we are using int point, which is some grid cell location xy, yi. And as the value, we are storing the grid cell data that represent their type, whether they are walkable or not, and maybe the cost, things like that. So for the navigation grid, we can use a map or an array. In our scenario, we are already using a map. Okay. So these are the data structures that you need to be familiar with A-star pathfinding algorithm when you are implementing it on real time at the Unreal Engine. Okay. So we have been already discussed all of this stuff. In the previous tutorial, we have discussed thoroughly about this priority queue and min heap, and we have been already implemented these maps and arrays. So we are good to go. Right. So algorithm is quite simple. Basically, it contains 4 major steps. The first one is basically we have to validate the start and target node to determine whether they are valid cells that can perform the pathfinding. And then we have to start pushing the start node to the open set, because that's the very first node that we are going to use for the traveling or the pathfinding. And then we have to keep looking to the open set, and until it is not empty, we have to check for these steps. So first we are going to select a node with the lowest F cost, because the open set is implemented as a priority queue. So the highest priority will be given for the F with lowest value, and we have to pick whatever the lowest value from that priority queue first. Then we have to determine that, or basically we have to check that whether that popped value or the popped cell data is the target. If it is target, then we already reached to the location, so we can stop the search. Otherwise, we have to continue pathfinding. So whenever we are continuing the pathfinding, first we have to move it to the closed set, because now we have been already visited this. So the closed set will be a simple array, and it will be pushed to this array. And after that, we have to evaluate all the valid neighboring cells. Okay. So neighboring cells means something like this. We have been discussed that as well. So let's just say this is our grid cell, and based on the movement type, the neighborhood cells could be different. So if I'm using the cardinal movement, the neighborhood cells will be the up cell, down cell, left and right cells. So if I'm using cardinal movement, because there are 4 possible movement types within that movement type. But if I'm using octile movement, Then addition to these 4 cardinal movements, there are intermediate movements as well, like this. So based on the cell that we are currently in, we have 4 or 8 different neighbors that needs to be evaluated. Okay. And likewise, we have to validate all the valid neighbors, right? Because some neighbors may not be valid, because let's just say if you are at the some sort of a border on the navigation grid, then of course the neighbors in these sort of areas are not valid. Or else let's just say there is a non-walkable grid or a blocked grid exist here, then of course that one is also not valid, right? So in such a scenario, maybe there could be like fewer neighbors who are valid to be traveled. So likewise, we have to evaluate all the valid neighbors and determine their cost to implement a path from start to target. And then we have to repeat this process until we find no nodes remaining and until we reach to the target. Okay, so that's the algorithm. And in order to implement this algorithm, basically right here at the open set, you need to be familiar with the knowledge of priority queue, which we have been already done. And in order to determine this cost, you have to be familiar with heuristics, which we have been already discussed. And in order to evaluate these neighbors, you have to understand the movement types, and that has been discussed as well. So we have discussed all the required foundational knowledge in order to implement this A-star pathfinding algorithm. Okay, so in case if you miss those topics, please go through those stuff, otherwise you will feel some difficulty whenever you are implementing this algorithm or even you are trying to understand it. Okay, so please go through those fundamentals first, then come back to this topic if you skip those parts. Okay, right. And this neighbor evaluation, I think I have been already discussed. Basically, based on the current cell that we are currently in, based on the movement type, the neighbors could be different, and their walkability will be also affect for the neighbors validity. Okay, and if we found a path from start to target, then we have to update this g cost, h cost, and we have to store those nodes in a proper data structure, and after that we can determine the best possible path. Okay, so these are like quite straightforward stuff that we have been already discussed. And once we find a path, we have to reconstruct it by backtracking it or reversing it, because usually the path will be constructed like this. So from the start to target, first we will evaluate this one and determine its cell value, this one determine its cell value, likewise until we reach to target, we determine the possible walkable cells. And after we find out all the possible walkable cells, we have to reverse it to determine the path to be traveled, so that we can jump from here to here to until it reaches to here. Okay, then the result is basically a clean path from start to target, which means a walkable path which is the shortest and optimum from start to target. Okay, and this path can be used for minimap path rendering or world map visualizations or even AI navigations. Okay, so in this course actually we are focusing on these two paths, minimap and world map path rendering and visualizations. And addition to that, actually you can implement the AI navigations based on the same pathfinding mechanism, right? Okay, a quick summary. So what is the advantages of A-star pathfinding algorithm? Well, basically it produces an optimal path from start to target by using the heuristics, and this is actually much more efficient than the brute force algorithms like Dijkstra. So Dijkstra is actually give the optimal path, but it is not that much optimized compared to the A-star pathfinding algorithm. So A-star is basically actually based on the heuristics, which means it is not evaluating the actual distances. So that's why it is much more flexible and faster. Okay, and these heuristics are customizable. That's again an important thing, because based on your scenario you can use whatever the heuristic that you want. And usually this is a industry standard for game development, and in other industries also which requires the pathfinding, such as navigation and transportation related industries also, these A-star pathfinding algorithm heavily used. And the time complexity is again very good. So in the best case scenario it is just O1 complexity, and in the worst case scenario it is ON complexity, which means even at the worst case we have a very good performance, it is a linear time complexity, and within the average case also, this is what we are usually rely on, we have a ON time complexity, but typically much more low. Right, so this is about A-star pathfinding algorithm, and up next let's take a small example to see how this computations works on runtime. And after, once we familiar with that example, we can go to the Unreal Engine and start implementing the A-star pathfinding algorithm.